You see a rusty piece of metal and you probably don't think twice about it. It just happens, right? But what if I told you that corrosion is this relentless, invisible enemy that's always working to turn our strongest metals back into literal dust? In this explainer, we're going to pull back the curtain on this unseen enemy.
So let's kick things off with a bit of a riddle. What on earth could a battery that powers your TV remote possibly have in common with a crusty old rusty nail? I mean, they couldn't be more different, right? One creates useful power, and the other is just decay.
Well, the answer to that question is a really big deal, because the global price tag for corrosion is estimated to be around 2.5, wait for it, trillion dollars a year. Yeah, trillion with a T. This is so much bigger than just an ugly fence. We are talking about the safety of our bridges, our pipelines, and pretty much every machine we rely on.
And here it is, the answer. Both that battery and that rusty nail run on the exact same invisible force, electrochemistry. It's all about the dance between chemical reactions and electricity. A battery is that force, tamed and put to work. Rust? Well, that's what happens when that same force is just allowed to run wild.
So what is corrosion, really? Deep down, you can kind of think of it as the world's slowest, coldest fire. Okay, so the official definition is the deterioration of a metal through an unwanted chemical attack. But that last part is what's really fascinating. It's the reverse of metal extraction. We pour massive amounts of energy into refining metals from their natural stable state in ores. While corrosion is just nature going, nope, I want that back, and trying to turn it back into a more stable rock. And you see this everywhere, right? That classic reddish-brown rust on steel, or that green film that gets all over copper statues and old brass doorknobs. Even the tarnish that makes a silver spoon look dull. They all look different, but they're all just faces of the exact same process.
To really, truly understand how rust works, we need to zoom in, way in. Because hiding on the surface of that metal is a tiny, unwanted battery that's just chugging away, causing all this chaos.
So check this out. This is a galvanic cell. Think of it as the basic instruction manual for any battery. You've got two different metals, some kind of conductive liquid called an electrolyte, and a wire to connect them. A chemical reaction just starts happening all on its own, pushing electrons from one side to the other. And that flow of electrons, that's electricity. Now, there are two main players in this game. First, you have the anode. A good way to remember it is A for attacked. This is where oxidation happens. The metal here literally dissolves, giving away its electrons. So in the story of corrosion, the anode is the part that gets destroyed. It's the victim. And on the other side, you have the cathode. This is where all those electrons at the anode released end up. It happily accepts them in a process called reduction. So while the anode is being attacked, the cathode is actually being protected. The electrons flow to it, not away from it. So in a simple battery, it's a three-step process. 1. The anode, let's say it's zinc, gets oxidized and gives up its electrons. 2. Those electrons shoot through the wire over to the cathode. 3. The cathode, say a piece of copper, accepts those electrons, and boom, the circuit is complete. You've got power. Simple as that. Okay, battery lesson is over. Now let's take that exact same principle and see how it plays out on a plain old piece of iron that's starting to rust.
And this is the mind-blowing part. A single rust spot is that galvanic cell we just talked about, just in miniature and short-circuited. All you need is a tiny little crack or an impurity on the surface. That little spot becomes the anode, the part that gets attacked and forms rust. And the huge area of metal all around it, that becomes the protected cathode. The metal itself is the wire, and a little bit of moisture is the electrolyte. It's a perfect self-contained rust machine.
Now this whole process gets put on hyperdrive when you have two different metals touching. This is called galvanic corrosion. Let's say you use steel screws on a brass fitting for a boat in salt water. Uh-oh. The steel is more active, meaning it's a much better anode. It will basically sacrifice itself, corroding away super fast to protect the brass cathode. But get this, you don't even need two different types of metal for this to happen. Sometimes all you need is a tiny difference in the environment. Think about a steel water tank. The area just below the waterline is starved for oxygen, right? That low oxygen zone becomes the anode and starts to rust away. Meanwhile, the area right at the waterline, with plenty of oxygen, becomes the protected cathode. And this same idea is behind one of the sneakiest, most dangerous types of corrosion, pitting. All it takes is a tiny piece of dirt to land on a metal surface. The area right underneath it can't get any oxygen, so it becomes a tiny but super powerful anode.
The huge surface area around it is the cathode. This massive imbalance causes that little anode to corrode like crazy, basically drilling a deep, narrow pit into the metal that you might not see until it's way too late.
So, yeah, it sounds pretty bleak, doesn't it? Like it's a battle we're destined to lose. But here's the cool part. If this destructive force is really just an out-of-control battery, can we use our knowledge of science to fight back? Oh, you bet we can.
I mean, just think about it for a second. If an unwanted battery is causing all this damage, what if we just plugged in our own battery? What if we could take control of the situation and force the electrons to go where we want them to go?
And that idea leads us to one of the most common and effective ways we fight corrosion: plating. It's literally like giving our vulnerable metal a custom-fitted suit of armor made from a tougher, more resistant metal.
This right here is electroplating, and it's where we essentially run that rust battery in reverse. We take the thing we want to protect, in this case a spoon, and we make it the cathode. We stick it in a special bath that's full of ions of our armor metal, like copper. Then we run an electric current through it, which forces those copper ions to plate themselves onto the spoon, creating a perfect protective layer.
Now, there are a couple of ways to do this. There's electroplating, which we just saw. That uses electricity. It works great, but only on things that conduct electricity, and it can be tricky to get an even coat on weirdly shaped parts. Then you have its cousin, electroless plating. This one is pure chemistry, no electricity needed. Its big advantage? It gives you a perfectly uniform coating on even the most complex shapes, and you can even use it on things like plastic.
So when you step back and look at the whole picture, it's kind of beautiful. The very same invisible dance of electrons that can slowly turn a steel bridge into dust is the exact same force we can harness to put a brilliant protective chrome finish on a car. The same force that destroys can also be used to protect.
It all just boils down to understanding and controlling that fundamental electrochemical reaction. And that really leaves you with a final thought, doesn't it? By mastering this one invisible process, we learned how to turn decay into defense. What other destructive forces in our world are just waiting for us to understand them so we can finally turn them into something amazing?